Hi, I'm Daniel Morgan, and we'll be covering the intent, benefits, requirements, and strategies behind rainwater management. The textbook definition of why LEED includes rainwater management as a credit is shown on the screen, but in a more straightforward way, increasing impervious area has an adverse effect on downstream water systems. Normally, when you develop an area, you will collect the rainwater runoff and convey the water through a storm piping system and eventually into a large body of water, such as a river or lake. This method would collect pollutants from the site and convey them downstream. So this LEED credit focuses on managing that runoff on-site, collecting the water and allowing it to filter pollutants through on-site green infrastructure and return the runoff to the groundwater table in a way similar to pre-development conditions. This graph helps illustrate why it is important to manage the quantity of water leaving a site. A pre-development runoff curve is shown in blue and a post-development runoff curve is shown in red. As you can see, the post-development curve has a higher peak runoff and a shorter amount of time to reach its peak flow, which, left unaddressed, is the reason why downstream flooding occurs. Some of the benefits to rainwater management are shown on the screen. Not only does this credit contribute cleaner water and groundwater recharge, but as the runoff hits impervious area that has been heated by the sun, the rainwater also heats up as well. Left untreated leaving a site, this warms the entire water system, having an adverse effect on plants and animals that need to live within a certain temperature range. Rainwater management also has an added community benefit because most strategies for rainwater management add green space to the site, which interrupts the urban landscape. LEED gives two options to address the requirements to comply with the rainwater management credit. The first option is addressing a percentile of rainfall events. So that is projects that elect to manage rainfall on their project site such that there is no immediate discharge after development for all rainfall events of a given depth. The second option is natural land cover conditions. So this means that the project will manage on-site the annual increase in runoff volume from the natural land cover condition to the post-development condition. Option 1 gives 3 different paths, and the first two address a 95 and a 98th percentile rain event to achieve either 2 or 3 points respectively, except the healthcare category, which gives 1 less point for each path. Path 3 addresses zero lot line projects, where projects whose building footprint aligns or nearly aligns with the site limits. If your project falls under this criteria, only an 85th percentile rain event will need to be managed. The reference manual offers a step-by-step guide to fulfilling this criteria. Step 1 is to determine if the project qualifies for a zero lot line path. This involves finding the floor area ratio of the project, and if the floor area ratio is less than 1.5, then the project is ineligible for Path 3 of Option 1. Step 2 involves obtaining rainfall data for the project location. You'll need to aggregate at least 10 years of historical rainfall data, and the BD&C reference guide provides recommendations on how to obtain this data. Step 3 involves determining the value for the chosen percentile of rainfall events. For example, if you choose the 95th percentile rainfall event, you need to refer to your data and find out where that 95th percentile lies and the associated depth. This chart shows why it is important to do these steps because given a different region in the United States or any project area, you'll have vastly different rainfall depths that you'll be using to design your site. Step 4 involves analyzing existing site performance. So the reduction in runoff can be achieved by protecting existing natural resources that serve to reduce the generation of runoff. So in this picture, they have developed a site layout for a church, but I've highlighted in yellow a section of the site that, left undisturbed, could contribute to reduced runoff on the entire site. Step 5 involves designing the site. You'll want to roughly lay out the site, including where permanent objects such as buildings will be located, and then examine the topography to identify where rainwater management features could be constructed. This layout can be refined in further steps. Step 6 involves calculating runoff volume to be managed on site. This involves hydraulic calculations to determine the amount of precipitation that the project will need to manage entirely on site through green infrastructure and low impact development techniques. Step 7 identifies how to manage runoff volume on site. So as the picture shows, as you collect water, there will be a water storage volume capacity. So that capacity can be no less than the amount of water needed to treat for your chosen percentile rain event. Anything past that can flow through an outlet structure into the water system. Step 8 involves analyzing and refining the proposed site design. As I mentioned in a previous step, once you find out exactly how much water you're going to need to treat and you may need to go back to your site design to resize some of the rainwater management features so that you're treating the proper amount of water. The lead guide also offers a step-by-step guidance for option 2, the natural land cover conditions. So this will compare the pre-development conditions to the post-development conditions and then treating the difference in runoff between the two. Step 1 of option 2 involves obtaining information about the natural conditions of the site. You'll need to gather information about how the site functioned prior to any development. This is important to get a hydraulic baseline of the site. Step 2 of option 2 involves calculating the natural conditions of the site. You will need to evaluate the pre-development historic rainfall data over a 10-year period. Step 3 involves calculating runoff volume to be managed on site. This involves using the pre-development hydraulic conditions found in Step 2 and comparing them to post-development site conditions of the proposed design. Any increase in post-development runoff will need to be treated on site. Step 4 of option 2 is similar to option 1, where you need to incorporate green infrastructure and low-impact development strategies into the site design to manage the on-site required volume of runoff. Some of the green infrastructure and low-impact development strategies to implement in site design are bioretention areas, porous or permeable pavement, cisterns, or green roofs. One example for rainwater management is bioretention. Runoff collects into a landscaped area that will provide temporary storage for the runoff until it is able to infiltrate through a filter soil mix and into the groundwater table. Porous or permeable pavements are drivable surfaces that are able to infiltrate water. However, this practice must be limited to lower traffic areas and areas without heavy truck traffic because of durability issues. Cisterns are containers or vessels that are used to store runoff for future use. Cisterns were modeled in cases where green roofs were not feasible or where it is necessary to include additional storage volume to meet the goal of on-site rainfall runoff capture. Green roofs are designed with lightweight soil media and planted with vegetation. The roof is able to store a limited amount of water in the landscaped areas. As the picture shows, the green roof is able to be turned into a walkable place for people to enjoy. I've included an example question as one would appear on the Green Associates exam. So the question is, what are ways to reduce water pollution from stormwater runoff? Choose 2. Open grid paving, impervious concrete hardscapes, rain gardens, or increasing the building footprint. I've highlighted the 2 answers in green, open grid paving and rain gardens. I've included references used to complete the presentation, and the EPA technical guidance on implementing the stormwater runoff requirements is an especially useful guide for rainwater management. Thank you.